Hey everyone, today I'm competing in Codeforces round 730. I recently made a couple of changes to my setup, which should allow for faster compilation, compiling and running my code while still in the editor, and then a bit of error highlighting when I compile. So hopefully all of that works out nicely, but let's see how it goes. Is this correct? Okay, that seems reasonable. Perfect. All right, awesome. Start. This seems pretty easy. Assuming I have the strategy right. I think this is actually easier than A. It's kind of funny. Of course I could be wrong, but no, I'm right. All right, well, that wasn't too bad. Oh boy, decimals, that's not fun. Okay, this seems like we could just do DP, I think. Okay, looks like I've got something wrong here. Oh wait, am I multi? Oh wait, no, okay. Oh. That would do it. Nope, still something going wrong here. Okay, so this one case is wrong. Oh. Oh, I see. I got it. Alright, I'm gonna increase the bounds just to be safe. So I don't know why my cursor is so light. That's kind of strange. Oh, whoops, I forgot to include it. Okay. Oh wait, oh I see, hold on. Yeah, this does not work. Okay, what's the nice way to do this? I guess actually brute force recursion would be fine. Oh, I need to multiply by the probability. No, okay, something's still going wrong here. I better run this in a full window. Hold on, how does this work? Oh, it's no longer a valid item if it ever reaches 0. I see. Alright, finally. That took me way too long. Yeah, we're past 15 minutes now. Yeesh, that's unfortunate. Well, that's what I get for misreading the problem. Anyway, let's see if I have any precision issues, which I think is entirely possible. Nope, I pass. Okay. Okay, and that's interesting. D is the interactive problem. What's the difference? many queries do you get? N. Oh, well, this is pretty easy, isn't it? Am I dumb? Okay, so oh wait, hold on, this is multitest. Alright, so we say the hidden password is chew. Alright, so 0 is not correct. Why is my program printing chew next? I feel like that should not be what's happening if I'm not mistaken. Oh. Alright, I'm just gonna submit this. Guess I'll do the small version first, but yeesh, I should have done this before C. Assuming this is right, obviously. Could have screwed it up somehow. Why is it taking so long? It's flushing the output consume that much time? I mean, the time limit is 5 seconds, so evidently the... Wait, WA on 1. Okay, does this property I'm thinking of only hold when... Oh, I'm dumb. Okay, so let's see. Okay, now let's see, which one of these do I need to swap out? I think both of them actually. So if val is odd, I think this should work, maybe. Alright, so here we're saying the hidden password is 3. It's not 0, and that doesn't change it. Does that change it? So let's see, so we're changing it to something such that 3 XOR, oh wait, no, so it becomes, oh, okay, I think this works. I'm at least confident enough to submit it. Yeah, there's a silly error, but I don't really have a big problem with it. I mean, it's not like it consumed all that much time. We'll see if it works this time though. Nope, okay. I'm assuming I just handled this special case incorrectly. Alright, I guess I should actually run the sample case now. 0. Okay, I think this makes sense, but it's also wrong, so let's see. Alright, so now we XOR, now let's see. Actually, so, let's see. Okay, yeah, this is not what it should be outputting, I think. Okay, let's see. Wait, actually, I think this is right. Does this make sense? I don't know. I'm gonna see if this works. It's like it doesn't really matter how many times I WA on one. Oh. Duh, why am I doing val percent chew here? Yeah, that's more like it. Alright. Not doing so hot this time. I feel like I'm coming up with the right ideas, but there have just been way too many dumb implementation errors. I mean, that just killed a good 10 minutes. I'm gonna assume that this is fine. Yeah, okay, good. Huh. Alright, this is kind of interesting. I haven't proven this particularly rigorously, but my conjecture is that the second part of the problem is only going to be possible when n is the power of 2. And if that's correct, I think I have a construction that maybe works. I'm just going to find this. Don't really know why this cursor is so light. It's actually kind of annoying, but oh well. Actually, you know what? Let's do it like this. Doing this set is going to be more efficient. Actually, I think we can go back to a vector. Actually, I think I do need to handle the n equals 1 case separately. All right. Okay, so I think this works. Not 100% certain, but I guess we'll see. Okay, this is clearly pretty sketchy. All right. Why am I getting this value? Wait, do I not have... No, I have multitest on. Okay, so the permutation part is wrong. So let's see, so we need y not to be equal to x and built-in pop count of y to be equal to I. Oh, shoot. Okay, there we go. Much better. And now let's run the last case. Okay, you know what? Actually, I'm just going to proof by AC this. Might get WA1, but we'll see. If it does, that's fine. Passes pretest 1. I'm kind of... Okay, cool. Passes. All right. Yeah, I'm not thrilled with my speed on this round. I feel like with C, D2, and E, I feel like I'm pretty happy with how fast I came up with the overall ideas, but but I took way too long to debug. I think I just misread C. For D, I thought there was a property of XOR that held in, or I thought this property of XOR that held in base 2 also ended up holding in base K for all K, and that turned out to be incorrect, which the overall idea was very similar, but I needed to make a few modifications. And then on E, I just had some implementation bugs. So that's a little unfortunate, but let's see how we did. Wait, did we win? Wow. Nice, okay. So I said all that, looks like we got first place. All right, well, hopefully we don't FST. That's definitely something I'm pretty concerned about given the lack of pre-tests. In fairness, they were all multi-tests. Like how many tests per file were there on each of these problems? 5,000, 10,000. Okay, so C is like mildly concerning because I feel like there could be some floating point precision errors that could screw me. What about D? 10,000, 10,000, and 4,000. Okay. Trying to decide if I want to stress test C. I'm kind of worried about my epsilon. It's basically the issue. No, I think this is probably fine. I know I am going to be a little frustrated if this ends up being an FST fest, but I also feel like, how many testers did this round have? Decent number. I mean, I feel like this would have FST'd, they would at least be aware of it. But I mean, the fact that there were only four in the first file, and then I'm going to assume 10 test cases per file, and I know I'm not thrilled with the fact that there are only 24 test cases here, but I feel like this is the sort of problem where they definitely should have had a lot more pre-tests. It's interesting, a lot of people have been saving C for the end, which I mean, I guess makes sense. And that's interesting. There's this huge gap between D1 and D2, which is interesting to me because I feel like I don't know, I definitely could imagine there being a lot of people like me where they come up with the observation, but then they realize you have to change it a little bit to get it to work for D2. But I actually feel like if you know the theory behind D1, then D2 is not that harder. But I also feel like I usually just have a tendency not to really see what makes subtasks easier in time to actually implement the small subtask first. So I don't know. And then E has not that many solves. I'm wondering if I just got pretty lucky with the observation there. But yeah, overall it was a fun round. I think as long as, I think it was one of the higher quality CF rounds in the last while, as long as you, as long as C doesn't turn into an FST fest just because of decimal precision issues. I actually feel like this would have been a better problem if they used fractions, perhaps. And I guess like maybe there was some sort of fixed denominator, and that way they could avoid all those precision errors because like obviously the error tolerance in the answer I don't think is going to be an issue, but what kind of bothers me is how an item like can become invalid, and then like that becomes a matter of testing whether something is exactly 0 or if it's just pretty close to 0. And I think that's a place where precision issues could come into play because doubles are not particularly good at testing exactly. I guess like actually maybe the strategy no. Let's see. I'm just curious. I'm trying to think if there's a way that I FST this. Because I have an epsilon of 1e negative 9, so I'm kind of wondering whether there's a way for something to go below 1e negative 9 but above 1. I'm pretty sure there isn't. Yeah, that wouldn't make sense because one thing be... Oh yeah, wait, no, what am I talking about? Yeah, there's no way. I mean, I'm not convinced this does an FST, but I don't think like the epsilon can possibly be too large. Okay, so I think I'm good. I'm not going to resubmit anything. It looks like Golovanov in second. We're just barely ahead of him. We got a little lucky here that the sample tests were strong because with both D and E, it's kind of annoying to figure out whether my results are correct by hand. And so it makes a lot more sense for me to just submit and then see if I get a C. Let's see, can either of these guys pass me? No, they can't. Okay, perfect. But yeah, I mean, that also is another reason not to resubmit because on these div choose, since they're unrated, I'm more maximizing the probability that I get first than I am maximizing like my expected score, minimizing my expected rank or anything like that. So honestly, I'm not really inclined to resubmit when doing so would drop me to, presumably like around this point. So it would drop me around 300 points, which would allow a whole bunch of people to pass me. But all right, yeah, fun round. So I guess I will go ahead and do solutions now. Okay, so problem A, exciting bets. So we have to maximize the so basically after you parse all the flavor text, we have to maximize the GCD of two numbers, given that we're allowed to increase both of them by 1 or decrease both of them by 1. And then we need to figure out the fewest number of those operations that we need to perform to achieve that maximum. I read these as long rungs, right? Yeah, I did. Okay, cool. All right. So the key here is for this problem is to understand the Euclidean algorithm, and what that says is that the GCD is that if given A is less than B, the GCD of A and B is equal to the GCD of A and B minus A. And so what that means, and then the other thing that we know here is we're increasing or decreasing A and B by the same amount. And if we increase A and B by 1, that means A goes up by 1 and B goes up by 1. But then B minus A doesn't change because B plus 1 minus A plus 1 is still B minus A. And so what that means is that B minus A is invariant under these operations. That is, it's going to be fixed no matter what. And so what that tells us is that if let's say that in the end the new value of A, after all of our operations, the new value of A is equal to X, the new value of Y is equal to B, the new value of B is equal to Y, then Y minus X is going to equal B minus A. And so the GCD of XY is going to equal the GCD of X, B minus A, and therefore it's necessarily going to be a factor of B minus A. Okay, so we know that the GCD is going to be a factor of B minus A, and so at that point the maximum possible answer is B minus A. And this is achievable whenever A and B are both 0 mod B minus A. And of course if A is 0 mod B minus A, then B, which is equal to A plus B minus A, is also going to be 0 mod B minus A, because both of these terms that we're adding are 0 mod B minus A. And so what that means is that we've reduced the problem to figuring out the minimum number of operations to make A congruent to 0 mod B minus A. And so basically there are two cases. The first is where we can decrease it until it's 0 mod b minus a, and that takes a mod b minus a operations. Or we can increase it, which takes b minus a mod b minus a operations. Because currently we're at a mod b minus a, and we need to increase it until it's all the way up to b minus a. All right, and so that ends up motivating the solution. So the first thing I do is I swap a and b if a is greater than b, because we've assumed throughout this process that a is actually less than b. So I'm just kind of enforcing that in the algorithm. And so then, just like I said here, I'm starting by printing out b minus a because that's the initial answer. And then if b minus a is 0, then I'm outputting 0. That's just a special case. If b minus a, or because if b and a are the same, then we can just increase them arbitrarily, and so and get an infinite result. And so in that case, the problem tells us to print 0, 0. And otherwise, I'm printing the minimum of the two cases that I described before. All right, awesome. Problem B. I'm actually curious. Let me take a look at the solve statistics. I personally feel like B was maybe not. I don't know if it's easier to prove, but I definitely feel like B was easier to solve than A. And I'm curious if other people are feeling the same way. It looks like their solve stats are about the same. Okay, that's pretty interesting. Anyway, problem B. So we have a set of values, and we want to rearrange them, or essentially, so we can. Let's see, what's the best way to explain this? So we have cars on a number of sections, and we can move cars between the sections, and eventually we want to minimize this summation. Okay, and so I guess the first thing to realize is that since we can move the cars as much as we want, the number of cars that are initially in each section doesn't actually matter. The only thing that matters is the number of cars there are in total, because then we can move them around however we would like. So so you'll see in my program that the first thing I do is I don't even store the number of cars in each section in an array. I just compute their sum, and that's because the sum is the only thing that matters here. Okay. Now I didn't write up a proof of my solution. I sort of went with proof by AC here just because I had a pretty strong intuitive sense that this is going to be correct. But my idea here is that we're essentially trying to minimize the sum of the differences between the numbers of cars in each section, and that means that you're going to want the numbers of cars in the sections to be as similar as possible. And what that leads to is you want them to distribute the cars as evenly as possible. And so what I did is that's exactly what I did. I distributed the number of cars as evenly as possible. And so that means, let's say that the sum is equal to a times n plus b. Then I placed a cars in n minus b sections, and a plus 1 cars in b sections. And intuitively, the way you can think about this is that you can think about it as we're giving 1 car to each section until we don't have n cars left. And at that point, then we're giving 1 car just to any b of the remaining sections, and then some of the sections will just not get another car. And so this distributes the cars as evenly as possible. And then we can quickly verify that the summation is going to be, so this term is going to be 0 whenever a sub I and a sub j are both a, or when they're both a plus 1. But when they're distinct, then this summation is going to be 1, because the absolute value of a plus 1 minus a is 1. And so what that means is that the summation is equal to 1 whenever we have one section in this case and one section in this case. And so the number of ways to pick one section in the first case is n minus b, and the number of ways to pick one section in the second case is b. So our answer is then going to be n minus b times b. I haven't written out a proof of optimality for this. For me, it just kind of intuitively makes sense that since our error function here is based on the difference between the number of cars in each section, our goal, we should be distributing them as evenly as possible. I'm sure that given a couple of minutes I could write something up, but I don't. But if you want to see a formal proof, it'll be in the editorial, at least hopefully. Some people do not put proofs in their editorial and in their editorials, and I think that's kind of silly. Okay, let's see. Oh yeah, I should go over my code. So here, it's pretty self-explanatory. I compute the sum, and then I mod it by n, and this means sum is essentially storing the variable b that I defined up here. And so then I print out sum times n minus sum. Yep, pretty straightforward. Make sure to store this in a long, by the way, because otherwise you might end up with an overflow issue. Okay. Anything else I want to go over here? Nope. I think I think that should just about cover it. Okay. So let's look at problem C. All right. So we have 3 kinds of items, and we're given the probability that we draw each item, and then this parameter v. And so at each step we draw one item at random, and if the item is of the 3rd type, then we terminate the process, and otherwise we decrease the probability of drawing that item in the future by v, and we redistribute that probability evenly among the other 2 categories. And we want to find the expected number of times we're going to need to make these draws. All right. So the general approach here is pretty much a recursive brute force. And so the first thing we want to do before we start coding up a brute force solution is we want to figure out, is a brute force fast enough? So the idea here intuitively is that C and M are just going to constantly decrease, and P is going to decrease. So let me express this more formally. So let's say we draw an item of type C. Then in most cases what's going to happen is the C is then going to decrease by V, and that probability is going to be evenly distributed among the other 2. So M is going to go up by V over 2, and P is going to go up by V over 2. Now the key idea here is that whenever we don't draw P, P increases. And of course when we do draw P, the process ends. So what we can think about is P is just going to keep going up and up and up until the process ends. And in particular, when P equals 1, we are definitely going to finish immediately. So that means that we can sort of bound the number of steps until P equals 1. Because in each step, when this is the case, whenever this happens, P is going to increase by at least V over 2. And we know V is going to be greater than or equal to 0.1. So that means P goes up by 0.5 every time we take a step of the first kind. And what that means is, and when P is equal to 1, we're done. So what that means is that we can say that we will make at most 20 moves of the first type, because when since if P increases by 0.5 20 times, P is going to be greater than or equal to 1. All right, so that means we're going to make at least 20 moves of the first type. And notice that after we make a move of the second type, the item that we drew is invalid. And so that means that we can only make one move of the second type with C and one move with V. And so at most 2 moves of the second type. And so that means we make at most 22 moves total, excluding the move where we draw P. And so that motivates a recursive solution, because so that means that a solution that has exponential runtime in the number of moves we make is actually going to be totally okay. And so in fact here we can intuitively we're going to need to keep simulating if we draw C or if we draw M. And what that means is that we can draw, or is that Sorry, I lost my train of thought. And what that means is that since we have 2 cases at each step, and we're going to need to make 22 steps in total, the number of states that we could possibly reach is bounded by 2 to the power of 22, and that's approximately 4 million, which is well within, which is definitely fast enough to run, since in 1 second we can run about 100 million operations, and so 10 test cases including 4 million function calls each should be fast enough. All right, so that means that we can do sort of a brute force solution, and obviously you'll generally want to pretty much always check whether doing a brute force solution is possible as sort of your first step on any problem, and usually it's not, but when it is, that can just make life a lot easier, and there are a lot of problems where it's really difficult to do much better than brute force. Yeah, so, and especially for weird problems like this, where it doesn't really seem like there's some sort of high n involved, like there's no parameter that's like n can be up to 100,000, a brute force solution can be really promising. So that's kind of the motivation for trying brute force, and then the explanation so far is essentially the proof that of the brute force's time complexity. Okay, so now let's go through my code. My main function is pretty simple. I just call the recursive function on the input values. So this go function is really where the magic is happening. So essentially, I initialize my answer to be 1, and that's to account for the next step we take. And then I break into and then there's basically 3 cases. One of them is where we draw C, one of them is where we draw M, and one of them is where we draw P. Now, if we draw P, the process immediately ends, so we don't actually need to do anything more for that case. But then I handle the case where we draw C. And so here, in this line right here, I make sure that C is actually something that we can draw, meaning its probability is greater than 0. And if so, I make this variable change that is equal to the minimum of C or V. And that's because if C is greater than or equal to, if C is greater than V, then if C is greater than V, then it decreases by V, and otherwise it goes to 0, which means it decreases by C. And so then I decrease C by this change, and then there's kind of 2 subcases here. So the first one that's going to happen most of the time is if M is still valid to be chosen, then M is going to go up by this change over 2, and P is going to go up by change over 2. But if M is already invalid, then all of this change is going to go to P, and M is going to stay the same. And so once I compute these new values, I increase the ans by C, the probability that we draw item C next, times this recursive call. And the case for M is essentially identical. So yeah, that's basically what's going on here. I should note, actually, I think I switched up these 2 operations. We actually only have at most 20 moves of the second type, because the second type is where we decrease by V. And then at most 2 moves of the first type. Sorry, I mixed those up. But yeah, that is about all there is to it. Okay, so let's look at problem D. So this problem essentially it defines base the XOR operation in base K for arbitrary K. And then we have a password that we know is between 0 and n-1 inclusive. And so, and we can try to guess the password up to n times. However, each time we make an incorrect guess, the password changes to a number such that, so if the password is currently X, and your guess is Y, new password is Z such that X, XOR the general, or usually we use the caret to abbreviate XOR, Z is equal to Y. Okay. Let's see. So the general process of solving this problem is what we're going to do is first we're going to say, okay, let's say the password is 0. Then we're just going to guess 0, and if that's correct, then we're done. Afterwards, we're going to say, okay, what if the password is 1? And then the password might have changed based on our past query. So what we're going to do is we're going to say, so actually here, let me write this down. So first query 0, then suppose the initial password was 1, query whatever the current password would be. And so for example, if k if k is equal to 3 and the initial password is 1, then after we query 0, the password is going to change to z such that so the password is 1 and we query 0, then the password becomes z such that 1 XOR z is equal to 0, and it turns out in base 3 that z is equal to 2. And so that we continue using the same process. So we suppose the initial password was 2, query whatever it would be now, and so on up until we reach n. So in general, we're just repeatedly thinking, okay, what if this was the original password? Let's just query whatever it would be now. And of course, we have n queries, so we can try every single possibility for the initial password. And so what that means is now we just need to compute what the so given an initial password, what would the password be after all the queries we've done so far? So we've reduced it to this subproblem. All right, so something that's going to be helpful to think about is we're going to want to in this equation, we're going to want to rederive z given x and y. And so just as a notational thing, I'm going to refer to XOR as plus, and then I'm going to refer to this sort of inverse XOR as minus. So like for example, I'm going to say x plus z is equal to y, and then that's equivalent to saying z is equal to y minus x. And so we want to figure out so it'll be helpful to figure out how we can perform this minus operation. And it turns out it works to just say, and so it turns out so first of all, we can look at this bit by bit, or I guess k bit by k bit. And so what we know is that if we assume z, y, and x are all single k-bit numbers, we have y equals x plus z mod k. And so if we subtract x from both sides, that means z equals x minus y mod k. And so that gives us a way to perform this minus operation. I can show you how it's implemented in my code in comparison to the main operation. So the plus operation is performed in this function, and what I do is I store the list of digits of the result, and so I take a mod k and b mod k and I add them and I mod the result by k, and then I divide both a and b by k, which essentially drops down to the next bit. You might be familiar with sort of going digit by digit like this in base 2 or base 10. So this is kind of a generalization of that approach. And so then I reverse the set of digits. So now I'm processing from the most significant digit to the least significant digit. And then I reconstruct the number from the digits. And in the minus operation, it's exactly the same, except I subtract b mod k instead of adding it. And then I also add this k here because the mod function, or the mod operator in C, is kind of weird when there are negative numbers involved. And so adding k ensures that the result is going to be positive without actually changing its value modulo k. Okay. So we have this subtraction operation. And so now let's think about what's going on here. So we query 0, so let's say that the initial password is x. After we query 0, the initial password is going to be 0 minus x. And so then what that means is now we're going to say, okay, what if the initial password was 1? And so we're going to query 0 minus 1. And I'm just going to call this P1. And so now let's say that that wasn't, or let's say that that guess is wrong. Then the new password is going to be P1 minus whatever the password was before that. So P1 minus 0 minus x. And so now we're going to take, and so now we take x equals 2. So we query P1 minus 0 minus x. And we're going to call that P2. And if that fails, the password is now going to be P1 minus 0, or P2 minus P1 minus 0 minus x. All right. Now, a key observation to make here that could be proven from the properties of the K XOR function is essentially that these minus and plus operations distribute in the same sense as our typical arithmetic operations do. And so what that means is P1 minus 0 minus x is actually equivalent to P1 minus 0 plus x. And likewise, this whole thing is equivalent to P2 minus P1 plus 0 minus x. All right, and so what I do in my program is I first I sort of maintain this part of the expression, and it's next, for example, we would have P3 minus P2 plus P1 minus 0 plus x, and so on. And then I either add or subtract x as the case may be. And so here, so Cx is where I store basically this current value here. And then if I is even, then here, so I'm in this loop, I'm checking whether I is the original answer. And so if I is even, then I add I, and otherwise I subtract I. And this K XOR is the addition, and K XOR M is the subtraction. And so then I query this value, and if the query is correct, then I return. Just because at that point we're done, and otherwise I subtract out whatever I subtract out our initial value from the current query. Okay, and so that gets through all of these queries. And then we are all finished. Let's see. Is there anything I'm missing or anything I can explain more clearly? I know some of this might be a little hard to follow, so definitely make sure to read the editorial if you're still stuck on any of this. But if you're still having trouble following after you read the editorial, feel free to leave a comment, and I will get back to you if I have time. All right, let's look at problem E. This one may be a little bit difficult to explain. All right, so we're given a we start with this n-dimensional hypercube. Then we permute it, and so then what we want to do is first we want to restore the hypercube, the original hypercube from the permutation, and second we want to figure out a way to color the vertices of the hypercube such that each vertex is adjacent to one vertex, or to exactly one vertex of each color. Okay, so let's start with the first part of this problem where we're trying to figure out the permutation. Now, the key way to think about this hypercube is let's say we have a vertex v. V is going to be adjacent to v XOR 1 or 2 to the power of I. For all I from 0 to n minus 1. And so this is something we can prove from the way the hypercube is constructed. It's also something that you can observe just by looking at the 3D example. Like, for example, 3 XOR 1 is 2, 3 XOR 2 is 1, and 3 XOR 4 is 7. And so those are the three things that vertex 3 is adjacent to. And so that's a helpful way to start thinking about the problem. And so then the other thing what that essentially means is that let's think about the vertices as binary strings. Then the adjacent vertices are the same string except with one bit flip. And it's like, let's say that, for example, we have n equals 4, or n equals 4, and we're looking at vertex 1, 0, 1, 1. Then the adjacent vertices are 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, and 1, 0, 1, 0. All right, awesome. So the way I ended up doing this construction is in increasing order of the number of ones in each bit. And so the first thing I do is I just say, okay, like let's just assume vertex 0 or vertex 0 in the permuted hypercube is vertex 0 in the original cube. Then what I'm going to do is I'm going to arbitrarily map the map the vertices adjacent to vertex 0 to the powers of 2. And that's because the vertices adjacent to 0 are, like if we have 0, 0, 0, 0, they're going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And that implies that, and all of these have only one bit equal to 1, and that means that they are powers of 2. And so for example, in this configuration here, I would map 0 to 0, and then I might map, for example, I might say, okay, 5 in the original hypercube was 1, 1 in the original hypercube was 2, and 7 in the original hypercube was 4. And this is a different permutation, obviously, from what they have here, but it also is valid. Okay, and so afterwards, we need to and the reason we can do this, by the way, is I'm not going to go through the full proof, but we can show that it doesn't really matter, or that it doesn't really matter which vertex in the permuted hypercube is mapped to 0, and which one is, and then it doesn't matter, and then the order of like which ones are 1, 2, 4, 8, etc. doesn't matter, and that's because essentially all of these numbers with only one bit are essentially equivalent in some sense. They aren't distinct in any meaningful way, and so we can order them however we want. Okay, so then the next step is I'm going to iterate over the numbers with at least 2 set bits in increasing order of the number of bits. And so then the idea is each number is going to be adjacent to to numbers with all but one of its bits. So for example, 1011 is going to be adjacent to 0011, 1001, and 1010. All 3 of the numbers that you get if you just remove one of its bits. And so what that means is we can look at these numbers. We can look at the numbers with fewer bits that it's adjacent to, and we can say okay, and we can actually like find all of the bits that are going to be in this number from those neighbors. And so that means that if all we know is that a vertex is the neighbor of 0011, 1001, and 1010, and we know that it's going to have 3 bits, then we can conclude that that vertex must be 101 or 1011 because all of these because these values are essentially telling us what bits are in our original number. Okay, and so I guess the one other step is you're going to need to actually figure out which numbers have, like for example, you're going to need to figure out which numbers have 2 bits, which numbers have 3 bits, and so on. But the idea is a number that contains k ones is going to be adjacent, or let's see, so a vertex that had k ones in the original hypercube is going to be adjacent to vertices with k minus 1 or k plus 1 ones in the original hypercube. And the idea is that if we flip a bit, we're either going to flip it from 1 to 0, which decreases the number of ones by 1, or we're going to flip it from 0 to 1, which is going to increase the number of ones by 1. And so by the time we process the vertices with k ones, we'll already know which ones have k minus 1 ones. And so we can say, all right, if a vertex doesn't have k minus 1 ones, then it must necessarily be one of our k plus 1 vertices. All right. So this process is essentially implemented in this main loop here. And so the idea here is I iterate over the number of, so first I just brute force the 0 case and then the ones with only 1 bit set. And then from here I iterate through the possible numbers of bits. And so then I iterate over the vertices with that number of bits. And from here, what I do is I go through the number of vertices with, or the set of vertices that are adjacent and that we haven't already found yet. So these ones must have more bits rather than fewer because we've already found all the ones with fewer bits. And then I go through their neighbors and I figure out which ones are, and I figure out like, okay, like which ones have we found already and which bits do we know are going to be in this number. And that allows me to reconstruct the permutation. This is obviously a fairly hand-wavy explanation, so definitely check the editorial if you're interested in more of the details. Okay, so the next step is this color idea. Now, I thought through this on paper for a little while, and the conclusion that I eventually came to, which evidently turned out to be correct. Why is there an announcement? Yeah, okay. And the key idea here is that, and the key observation here is we have to figure out when doing this coloring is actually going to be possible. And what I figured out is that the coloring is possible only when n is a power of 2. I don't have a formal proof for this. I was able to prove that the coloring isn't going to work for any odd number greater than 1, and I'm guessing that you can just kind of extend the same logic. But I came up with a really nice construction that worked pretty cleanly when n was a power of 2, and I sort of just guessed that was going to be the best way to do it, and that it would only work when n is a power, and so then there wouldn't be like a different construction that you could use when n wasn't a power of 2, and that guess turned out to be correct. So basically, the idea of the construction is I take like the numbers of the bits that are set. So for example, going back to this 1, 0, 1, 1 example, these bits, we're going to call them 3, 2, 1, and 0 in that order. And so what I do is I just take the exclusive OR of all the bits that are set. So for this number, I would take 3 XOR 1 XOR 0, which is 2, and so 1, 0, 1, 1 would be colored 2. Okay, why does this work? So the basic idea here is that flipping any bit is equivalent to XORing the color by that corresponding bit. And so for example, if we were to flip this bit 3, we would get 0, 0, 1, 1. All right, which has color 1 XOR 0 equals 1, and indeed 2 XOR 3 is equal to 1. And so that means that in general, the adjacent vertices are going to have colors equal to, so if we're at a vertex with color C, adjacent vertices will have colors C XOR I for I from 0 to n minus 1. And then a good fact to know about the XOR operation that I would encourage you to prove if you haven't seen it before is that when n is a power of 2, C XOR I will be distinct for all I from 0 to n minus 1. So that this XOR based coloring is going to be mean that all the neighbors of each vertex have distinct values. Yeah, more details on that in the editorial, but this works pretty nicely when there are powers of 2, or when there are powers of 2. Otherwise, it completely breaks whenever n is not a power of 2, and so in those cases, I just print -1. So yeah, that was the contest. Hopefully, this explanation makes some sense. I know they're a little hand wavy and don't go into as much detail as you might like, but they might hopefully be a good give you a good general idea of how I thought about these problems. If you're interested in more detail, read through the editorial, and if you still have any questions after you do that, please feel free to go ahead and leave a comment. But yeah, I think that's about all. Let's go ahead and take a look at the standings just before the contest finishes. Looks like only 13 AKs so far. Several actually have everything except D, and it's interesting. I'm actually pretty surprised. D1 has nearly 10 times as many solves as D2. Actually, I think I misspoke. A few people have everything except C. How are my friends doing? All right, awesome. So yeah, I think that is about all I have. So thank you very much for watching, and enjoy the rest of your day.